Now that we've determined the discharge conditions of the turbine and the bypass stream, we're ready for the mixer where we join those two streams together again. And we can calculate our total temperature here really based on an energy balance of their two streams. Once again, we've kind of got a formula that's already solved out the energy balance. So it's going to be 1 plus F, our fuel to air ratio, times the specific heat at the mixer of the core stream times TT5 plus, again, our split ratio, our duct split ratio, which tells us how much of the bypass duct is exhausted and how much is carried in and mixed through with the core, times our bypass ratio, times CP at the mixer for the bypass stream, times TT 7.5, the discharge temperature of the duct, and that all divided by 1 plus F times, again, our core value of CP plus the split ratio times the bypass ratio times the bypass value of CP. And so this, in the core, we're going to be evaluating that at the average temperature, evaluating those properties at the average temperature of TT5 and TT 5.5. And for the bypass, that's going to be the average of TT 7.5 and TT 5.5. So since both of those properties depend on the number we're actually solving for, that once again means that we will need to integrate to evaluate a couple of our other parameters here. We need to know F, our fuel to air ratio, which is going to be equal to m dot fuel over m dot of our core air. So that's going to be, we already calculated the flat mass flow rate of fuel when we were doing the combustor section. So 3.661 pounds mass per second divided by the actual airflow rate through the core, which we knew from the beginning is 155 pounds mass per second. And so that'll give us fuel to air ratio of 0.0236. And the other parameter we don't yet have is our duct split ratio sigma, which, remember, is defined as the bypass mass flow rate over the bypass mass flow rate plus the area out through the exit nozzle, m.9. And so here we I'm sorry, m.9 being the bypass exit, bypass fan nozzle. So if we had an exhausted fan, there would be a mass flow there. In this case, since we have a fully mixed turbofan, that m.9 is going to be equal to 0, and we're left with just the mass flow rate through the bypass duct over the same value, so we're going to have a split ratio of 1. And so once again, we're going to need to iterate. We're going to start out with some guess of TT5 in order to evaluate our specific heat properties here, and then we'll use that guess to calculate a new temperature of TT5, and then again feed that back to update our air properties. So looking at iteration here, we're going to guess a value of just 1800 degrees Rankine for TT5 and use that for the core and bypass streams to calculate the values of CP that we need, and use that to update our value of TT 5.5. That then gets repeated on the next line down, and we use that as the input to determine our air properties again, and that'll very quickly converge. So we get that after the mixer, the total temperature of 5.5 is going to be equal to 796.218 degrees Rankine, and the pressure is Not too hard to determine. Got PT 5.5 is going to be equal to our mixture pressure ratio, which is accounting for any total pressure loss through the mixture, times PT5, our turbine discharge pressure. So we'll have 0.99 is our given mixture pressure ratio times the turbine discharge pressure, 9.638 psia. So our new total pressure coming out of the mixer is going to be equal to 9.541 psia.